Good evening everyone. Today I am going to explain the chemistry of borohydride. This is the second part. Please see the part 1 also. I will give the link in the comment box. So I am Tanmoy. I am currently doing my PhD at the Ministry of Science, Education and Research, Kolkata. So today we will discuss mainly about the borohydrides and their reaction with organic molecules. So before going to details, let's check about the borohydrides. This is borohydride with a formal negative charge. This is sp3 hybridized. Okay. So it is mainly a useful reagent for reduction like carbonyl compounds. But before going to details, we will discuss how to tune the reactivity of borohydride. You can see this borohydride is attached with 4 hydrogens, and for reduction we need at least 1 hydrogen. So we can maximum change these 3 hydrogens or minimum replace this 1 hydrogen among these 4. So for example, let's consider R1, R2, R3. Okay, and in case for counter metal cation, we mainly consider as sodium plus or lithium plus. Okay, so first let's focus on this 3 substitution. So we can see this borohydride contains delta negative hydrogen and delta positive boron. So it is expected that this delta negative may react with water, alcohol, these reagents. So if the negative charge density on this hydrogen is more, then it will react more efficiently. So we will get more active hydride transfer reagent. And if the negative charge density over this hydride is less, that will be little less reactive. Okay, then how can we make it more electron rich, and how we can make it less electron rich? Okay, so simple strategy is to increase the electron density. Let's put the group which are by itself electron rich. For example, ethyl group C2H5. Why I am telling ethyl? Because already an established reagent is there containing ethyl group, where R1 this R1 equal to R2 equal to R3 equal to these 3 are ethyl group, one reagent, and that the corresponding actual reagent is lithium C2H5 thrice BH. Okay, this is the reagent. Similarly, let's substitute this with the electron withdrawing group, and here we will replace one R with the electron withdrawing group. For then, what will be the reagent? That is, if R1 equal to Cn and both R2 and R3 equal to hydrogen, then we will have a reagent named as sodium cyanoborohydride. Okay, so ultimately this substitution we got sodium cyanoborohydride. And similarly, another type of variation we can make. For example, here we take R1 equal to R2 equal to R3 equal to isobutyl. Isobutyl means this. Okay, substitution is here, or we will consider it as a IC4, and this simple alkane formula is 2n plus 1, so H9, and the corresponding reagent is lithium C4 H9 thrice BH. Similarly, if we consider that the sodium counterpart of this such type of little less reactive reagent, that is R1 equal to R2 equal to R3 equal to OMe, methoxy, and the corresponding reagent is Na OMe thrice BH. Sorry, here should not be BH4, this should be BH3. So this is the reagent. So I guess you have understood the reactivity variation to get different reactive reagent. So right now we will check the reactivity, at least reactivity difference of at least one pair of this reagent. For example, let's consider about this lithium triethyl borohydride. So this reagent is very much reactive and react violently with alcohol or moisture, water or alcohol. Okay, and this reagent will react very less or slowly. This is very less reactive in water and alcohol. Why? Because the cyano groups reduces the electron density on this reduces the negative charge density on the hydrides. That's why its reactivity decreases. It reacts very slowly. But instead of that, this ethyl group, which has a plus I effect, which increases the electron density on the negative charge density on the hydride and resulting into more reactive hydride. And last video I have also explained that this hydride plus the delta plus of this proton from water molecule reacts, and actually this reaction is like H minus and H plus, which will ultimately produce hydrogen gas. So this happens, and that is the main reason for this violent reactivity. Okay, I guess up to this you have understood. Now we will check the role of these two metal centers, that is sodium and lithium. Okay, how this reacts. If you check, for example, if you take sodium borohydride versus lithium borohydride, here the main the borohydride part is same. Actually, that center is reducing, but changing the metal center, that reactivity differs. Why? Because the metal is actively playing some role. How? If let's compare the sodium and lithium first. We know if we go the first period, then first is hydrogen, then lithium, then sodium, and we know that going down as row in a periodic table increases size. So here in case of sodium, from nucleus there are two layers. Here 2 electron, here 8 electron. But in case of lithium, here only one shell is there from the nucleus with 2 electrons. So you can say that any molecule with having some electron density will be attracted more towards this lithium center compared to this sodium center, because this lithium is also a singly positive charge and sodium is also a single unit positive charge. And how and this thing is reflected, this thing is the main reason for the difference in reactivity of this lithium borohydride and sodium borohydride for this conversion. As for example, let's take about this ester. And reduction of this ester into this. If we take lithium borohydride, then this reduction is possible. But if sodium borohydride is taken, this sodium borohydride can't achieve this reduction. Let's take an amide, that is CONHR prime, and similarly using that lithium borohydride, this reduction happens to R CH2OH plus R prime NH2. But sodium borohydride is not capable to do this conversion. So this clearly indicates the reactivity difference of sodium versus lithium. Okay. Okay, let's focus about the one of the most important reaction of this borohydride, that is reduction of carbonyl group into alcohol. For example, if we take a ketone, it will produce a secondary alcohol. So, how this reaction is happening? These borohydrides contain 4 hydride with a nuclear charge, and we can consider this borohydride as a combination of BH3 plus H minus, because in my previous lecture I have discussed that borohydride reaction of this diborane, that is a dimer of this BH3 with lithium hydride, produces lithium borohydride. So you can consider this as a combination of BH3 and H minus, and that's why this A, and here this hydrogen is in sp3 hybridized orbital, consequently more nucleophilic, so it reacts here and opens up this ring. What happens? And ultimately this product is produced. So what's we are saying, it's a reduction reaction. So where is the reduction happening? Because for example, H minus and this H minus in hydrogen's oxidation state is -1, in H minus hydrogen's oxidation state is -1, and this carbonyl thing, if we consider it as a carbon and carbon, so oxidation state of this carbon is +2. Here oxidation state of this carbon is 0, and that hydrogen which attached here has +1. So ultimately this one is getting oxidized and this carbon is getting reduced. That's why we call this as a reduction reaction. Okay. Let's discuss about some question in this context. For example, this is acetone plus sodium borohydride this, and another thing, reaction with this with D3O plus, then the obtained product react with D3O plus and to produce another product. Okay, so D3O plus, or we can consider as a DCl in D2O. Okay, what will be the product? Let's give 4 options. And then we need to know how the reaction is happening. First of all, this hydride is attacking that carbonyl group. So hydride from this boron attacking here and open up this ring. So this product structure is this, sorry, it should be single bond O minus and corresponding Na plus. Now when you are putting acid, that is a deuterate acid, you must be careful here. It is a deuterate acid. Then what will be, then this alkoxide will be hydrolyzed and it will take deuterium from the solution, and the product structure will look like OD. Okay, I guess it is pretty simple. This question is pretty simple. Let's complicate the problem a little bit. Instead of BH4, let's take BD4. It's a deuterated borohydride. Here also let's take D. Then I guess you can do the answer very easily. Here D, and ultimately that product also contains D. Let's vary the question little bit, one extent more. Instead of this D3O plus, let's take H3O plus. Then here will be D, here will be H. So what is the reason to give this problem? To give you a message, always keep in mind that hydrogen attached to this carbonyl carbon or this should be come from borohydride. Okay, and hydrogen on this oxygen should come from water. So some MCQ question would be given to you which will confuse you. So I guess it will be better if you can remember this thing. So formally this is the end of the video. If you like my videos, please give me a thumbs up and subscribe my channel Chemistry, the Mystery of Molecules. So before going to finish this, I want to give you a question which I shall explain in my later video. But before that, I expect that you should try by yourself. The question is, why lithium aluminium hydride is stronger reducing agent than sodium borohydride? Okay, this is the homework. So I expect that you should try this thing by yourself, and next video I will explain the answer. And another thing, in next video I shall explain some about this lithium aluminium hydride. Okay, so bye bye for this lecture. Take care.